Before we dive into the strangest story about crabs you've ever heard, hit that subscribe button and give this video a like. It really helps this channel keep exploring the weirdest corners of biology and the cosmos. Now, let me ask you something. You think you know what a crab looks like, right? Hard shell, claws, scuttling sideways across the sand. Well, here's a fact you probably never heard. Most of the animals you think are crabs, they're not crabs. They're imposters. The coconut crab? Not a real crab. The king crab? Not a real crab. The porcelain crab? Also not a real crab. They are all fakes. And the strangest part? They're not even pretending to be crabs as part of some family reunion. They evolved this shape completely independently, one after another, over hundreds of millions of years. Evolution keeps turning completely different creatures into the same form, into a crab. This phenomenon even has a name, carcinization. It literally means crabification, and it poses a question to biology that still doesn't have a final answer. Imagine the Pacific Ocean about 10 million years ago. Somewhere off the coast of what is now New Zealand, a spiny creature with claws is crawling along the seabed. Scientists call it Paralomys dibodiorum dash. It's an ancient ancestor of modern king crabs. It was about the size of a baseball, wore a round shell, and apparently preferred deep, cold waters. If you saw it today, you'd immediately say, well, that's a crab. But it wasn't a true crab. This creature belongs to a huge group of crustaceans known as Animura. This group includes coconut crabs, porcelain crabs, and hermit crabs. They all look similar, but not one of them is a true crab. They descended from long-tailed creatures that looked more like shrimp or lobsters. And then, independently of each other again and again, they evolved into the shape of a crab. But why? Why does nature keep repeating this form? What's the secret of its evolutionary success? Why do other species keep trying to copy it? The answer lies in the surprising efficiency and flexibility of this body plan. About 360 million years ago, the first decapod crustaceans appeared. They crawled on muddy seabeds and looked like modern lobsters. Around 260 million years ago, their family tree split into two branches. One branch became the true crabs. The other became the false crabs, the impersonators. Time passed. In both groups, the same process began. The long lobster-like tail gradually shortened and curled under the shell. The narrow body became flat and wide. From a survival perspective, this was a breakthrough. Scientists even call it the Cretaceous crab revolution. Nearly 80% of modern groups of true crabs originated right then. And crab-shaped creatures occupied far more ecological niches than their long-tailed relatives. The reason is versatility. A flat, round body lets you walk, run, swim, burrow into sand, and even climb trees. A lobster or a shrimp can't do that. They're limited in their movements. What's more, by hiding the long tail, the animal removed a convenient target for predators. Life in the form of a crab allowed animals to colonize completely new habitats. Mobility plus protection, a powerful combination. Natural selection came back to the same solution again and again. In the end, carcinization is an example of convergent evolution. That's when completely different organisms, without any coordination, arrive at the same engineering solution. The crab shape turned out to be a universal key to survival. Nature always seeks the most optimal path. And it seems that becoming a crab is one of its most successful design tricks. This leads to one of the deepest questions in biology. And it sounds like this: if we rewound the tape of evolution and started it over from scratch, would we get the same result? For a long time, many thought no, that life on Earth is a chain of accidents. If the asteroid had fallen a few thousand kilometers to the left, dinosaurs might have survived, and we wouldn't be here. But here's the thing. At least 5 times, independently of each other, evolution has arrived at the same body plan. Not because species swapped genes, but because the laws of physics, gravity, the density of water, the pressure of predators create the same problems. And the optimal solution is the same. That's convergent evolution. And crabs are far from the only example. Eyes have evolved independently at least 40 times, invertebrates, insects, mollusks, and jellyfish. The designs are different: lens eyes, compound eyes, mirror eyes. But the problem is the same. Capture light and build an image. Or take wings. Insects, birds, bats, extinct pterosaurs all invented wings independently. for completely different solutions. But all four are about the same thing: how to get off the ground. This brings us to the main question. If evolution on Earth is obsessed with certain solutions, will it be obsessed with them on other planets as well? Zoologist Ari Kirschenbaum from Cambridge, in his book, The Zoologist's Guide to the Galaxy, argues yes. The laws of physics are the same everywhere in the universe. The problems life faces, how to move, how to get energy, how not to get eaten, are universal. If the same solutions keep arising on Earth, there's no reason they wouldn't arise on another planet. He says that animals on other planets will likely have legs, though he can't say how many. That's a matter of chance, though almost certainly an even number. So what do aliens look like? Possibly not so different from us. If on a distant planet with oceans and predators something is slowly tucking in its tail and flattening its shell right now, don't be surprised. You already know how that ends. But here's the twist. We've just talked about body shape, shells, claws, wings. What if shape isn't the most important thing? What if the most interesting thing that evolution repeats isn't the body, but the mind? Here's a riddle. On a distant planet, there is a creature. It has no backbone, no skull. Its nervous system is distributed throughout its body. It can change the color of its skin in 200 milliseconds. It can solve problems that would stump a 5-year-old child. It communicates through touch and texture, and it lives for about 2 years. Question: is this a description of a hypothetical alien, or of a real animal crawling right now on the bottom of the Mediterranean Sea? You can't tell. That's the point. For centuries we've looked at the sky and wondered what alien intelligence looks like. Meanwhile, it's sitting in a crevice of the Great Barrier Reef, staring back at us. That creature is the octopus. The octopus has 3 hearts, blue blood, and a donut-shaped brain through which its esophagus passes. 2/3 of its neurons are not in its head but in its arms. Each arm essentially makes its own decisions. It's not a brain with a body, it's a network of 9 semi-autonomous processors. And yet the octopus opens jars from the inside, recognizes individual human faces, escapes from aquariums at night, sneaks into neighboring tanks, eats the fish, and returns home. In a lab at the University of Otago, an octopus named Inky removed the lid of his tank, crawled across the floor, slithered into a drainpipe, and escaped to the ocean. He planned his escape. The last common ancestor of humans and octopuses lived about 750 million years ago. It was a flat, blind creature the size of a grain of rice, with no brain and no eyes. Everything the octopus has, its eyes, its intelligence, its ability to solve problems, evolution built from scratch, independently of us in parallel. And here's the astonishing part. The octopus's eye is built almost like the human eye.
A lens, a retina, a pupil.
In one respect, it's even better. The octopus has no blind spot. Its retina isn't turned inside out like ours. Evolution solved the same problem, but better. We're used to thinking that intelligence is an accident, that we just got lucky. An asteroid killed the dinosaurs, mammals emerged from the shadows, and after a million lucky coincidences, a brain capable of building rockets appeared. But the octopus says, no, complex intelligence isn't a lottery ticket. It's another crab, another form that evolution keeps returning to, because the task of understanding the world is universal. If intelligence is convergent on Earth, it's convergent everywhere. To understand aliens without wild fantasies, we need a rule. That rule is, form follows function. How an animal looks depends on how it lives, how it finds food, how it reproduces. Look at Earth's animals. The elephant's trunk, the narwhal's tusk, the bright colors of butterflies and wolves. Almost every feature serves a purpose, giving a survival advantage. Nothing arises just because. Of course, biology has accidents. Sometimes a trait sticks randomly, especially in small, isolated populations. That's neutral evolution. But such random traits are usually small and unnoticeable. Evolution won't tolerate flashy, meaningless decorations. They cost energy and attract predators. Animals look different because they solve different problems. Bright color attracts a mate or warns a predator. Huge size defends you. Stealth helps you catch food. We can't say exactly what aliens look like, whether they're green or gray-brown crimson. We don't even know if our eyes could perceive their colors. But we can confidently predict what problems they face on their planet. From those problems, we can understand that their diversity will be as great as Earth's. And how they adapt to their environment, how they behave, that's far more interesting than their appearance. In behavior, we're most likely to find common ground with them. So to understand aliens, we need to look not at form but at function. And here, natural selection is our guide. It's arguably the only coherent explanation of how primitive slime over 3.5 billion years turned into all this incredible complexity. The principle is genius in its simplicity. Successful solutions are preserved, unsuccessful ones are discarded. Richard Dawkins gave a great example. Imagine you randomly type 20 letters on a keyboard. The chance of getting a meaningful phrase is 1 in a million billion, almost impossible. But now change the rules. Randomly change one letter at a time. If a letter happens to match the target phrase, keep it. With this approach, the meaningful phrase will assemble in just a few hundred tries. Nature doesn't have a pre-written phrase, but it does have a criterion, better or worse. If a change helps survival, it sticks. Natural selection is like climbing a mountain in thick fog. You can't see the summit, but you can feel which way is uphill and take a step. Blindly, slowly, step by step. Mathematics proves that in such conditions, there's no other way to the top. Science has no real alternative to natural selection. Ideas about a vital force, a divine plan, or the matrix explain nothing in terms of mechanisms. Moreover, we can describe natural selection mathematically. George Price derived an equation showing how quickly a trait spreads depends on how beneficial it is. If long teeth give a huge advantage, they'll spread like wildfire. If the benefit is dubious, evolution crawls. Astonishingly, Price's math doesn't care whether it's happening on Earth or on Saturn's moon Enceladus. It's a pure rule of nature, and it works everywhere. Given that the universe had a beginning, the Big Bang, life somewhere must have started from absolute zero. The only known way to climb from zero to superintelligence is good old natural selection. You might ask, how can we be so sure that our Earth-based knowledge applies to aliens? It's all about one rule. Under similar conditions, evolution finds similar solutions. That's convergence. Look at birds and bats. They can fly, but their last common ancestor lived 320 million years ago, before dinosaurs, and certainly couldn't fly. Birds and bats learn to fly completely independently, and they're not alone. Flight was invented at least 4 times. Birds did it 150 million years ago. Bats did it about 50 million years ago. Before them were the giant pterosaurs and of course insects, which first took to the air 350 million years ago, just to avoid breaking when they fell from trees. Birds have feathered wings. Bats have skin stretched over elongated fingers. The construction is different, but the function is the same. Chasing insects like crazy. Flight is so advantageous that nature invents it again and again. The same goes for the lens type I, which evolved independently at least 6 times. The ability to deliver electric shocks evolved just as many times. Live birth has been invented more than 100 times. The most vivid example is the thylacine, the Tasmanian tiger. It looks exactly like a dog or coyote, but genetically it's closer to kangaroos and koalas. How? Because the thylacine in Australia and the wolf in Eurasia occupied the same ecological niche, the large predator niche, and evolution sculpted surprisingly similar creatures from completely different ancestors. That's why convergence is our key to cosmic zoology. The same problems that made Earth animals grow wings or fangs will make aliens search for similar solutions. That doesn't mean other planets will have exact copies of our wolves and kangaroos. The famous biologist Stephen Jay Gould loved to say, if you rewind the tape of life and play it again, the result will be different. Evolution is not just predictable rules. It's also full of accidents and catastrophes. Remember the asteroid that likely killed the dinosaurs 66 million years ago. If it had hit a bit to the right, reptiles might still rule the world, possibly even intelligent ones. And 250 million years ago, there was the even more horrifying Permian extinction, which wiped out 90% of all species. So what rules can there be if everything depends on a stray rock from space? But here's the thing. After that monstrous Permian extinction, life recovered in just 10 million years. Yes, the famous trilobites that crawled on the ocean floor disappeared forever. But the ocean floor didn't go anywhere. Food was still there, and that empty niche was quickly filled by crustaceans or crabs. When the planet empties, surviving species start to change rapidly and occupy the vacant spots. That's adaptive radiation. Forms change. Instead of giant reptile-like beasts, dinosaurs arrive. Instead of trilobites, crabs come. But the functions remain the same. Someone has to eat grass, someone has to hunt, someone has to crawl on the seabed. So we won't meet an exact copy of an earth fox in space, but we almost certainly will meet a medium-sized cunning predator that does the same job. Life may not repeat forms, but it always repeats functions. Now let's dig deeper. What universal laws does convergence rely on? The main one is natural selection. It works wherever three conditions hold. First, offspring inherit traits from parents. Second, those traits vary between individuals. Third, those differences affect how many offspring you leave. That's it. If those three conditions are met, selection works flawlessly on Earth, in a computer simulation, or on an alien world. But modern evolutionary biology has gone far beyond simple survival of the fittest. We have complex mathematical models, and this raises doubts. Are those extra layers too Earth-specific? Will they work in space? Consider two striking examples: sexual selection and kin selection. Look at a peacock's tail. It's a disaster for survival, hard to fly with, easy for predators to spot. So why does it exist? Only to attract a mate. The same with deer antlers or birdsong. That's sexual selection. Animals are willing to risk their lives to leave offspring. Now look at meerkats. Subordinate females often give up their own reproduction to raise the pups of the dominant female, their sister. That's kin selection. Animals help those with whom they share genes. It's the foundation of any complex society. But both peacock tails and meerkat societies are tied to something that seems very Earth-specific: sex. Honestly, scientists still don't fully understand why sex exists. Without sex, reproduction seems much simpler and more efficient. No need to waste time courting, and children get 100% of your genes instead of half. Yet it's sexually reproducing creatures that have created all this incredible diversity on Earth. Bacteria, which just split in two, remained simple single-celled blobs. So why did evolution invent sex? There are many hypotheses. Constant gene mixing might be the only defense against fast-mutating parasites, or a way to adapt faster to sudden climate changes. As aphids do, they clone in summer but switch to sex in winter to produce genetically diverse offspring, hoping someone survives. But most importantly, sex creates complex social structure. In a clone colony, everyone is 100% related. There's no conflict of interest, no difference between your child and your neighbors. But when sex appears, relatedness varies. My child is closer to me than my nephew. From that difference arise family, competition, alliances, hierarchy, all the complex behavior that makes us human. So, do aliens have sex? We don't know, but it doesn't matter how many sexes, 2 like us, or thousands like some fungi. What matters is the principle of shuffling genetic information between individuals. If complex multicellular life exists on another planet, it almost certainly uses an analog of our sexual reproduction. Otherwise, it couldn't evolve into anything interesting. This returns us to the main idea. It doesn't matter what chemistry alien life is based on: carbon and water, or silicon and liquid methane. The fundamental forces of evolution don't change. When paleontologists dug up ichthyosaurs, they could understand how they lived even though they'd never seen one alive. Those ancient reptiles were aliens to them. In the same way, we can predict alien behavior knowing the universal law of selection. Forms may be anything, but functions, the rules of the game in the universe, are the same. Take movement. How do animals get around? The laws of motion are universal. To move, you need to apply force. You can push against solid ground, like a worm through soil, but that's hard. It's much easier to move through something that flows, either a liquid or a gas. In any fluid, an animal has 3 options relative to gravity. First, you're heavier than the fluid, so you sink. Your fate is to walk on the bottom or on land. That's us dogs, crabs. We walk at the boundary of solid and fluid. Birds are heavier than air, so flight for them is a constant battle against falling, stop flapping, and gravity wins. Second, you're lighter than the fluid, so you float. A seal finds it easier to lie on the water surface than to dive, to go down. It has to fall upward, expending effort. The Portuguese man-o-war has a gas float and spends its whole life on the surface, unable to descend. Third, neutral buoyancy, the jackpot. Your density equals the fluid's. You neither sink nor float. You don't waste energy fighting gravity. That's what fish do. They adjust their weight with fat or a swim bladder. Now, when you're suspended in water or gas and start moving forward, the fluid flows around you. If you have fins or wings, you can change their angle and the flow itself pushes you up, down, left, right? That's incredibly efficient. Think of dolphins' crazy turns or flocks of birds in the sky. It's hard to imagine that only on Earth did animals discover the huge advantages of dynamic movement in a fluid. So other planets probably teem with, well, not fish, but some animals with a similar swimming method. But how do you get moving when you're hanging in air or water with no solid ground under your feet? The most obvious way is to flap wings or fins, pushing the fluid backward. Birds and fish constantly change the shape of their wing or fin during a stroke. They also use vortices. When a fish swings its tail, it creates swirling rings of water behind it, like smoke rings. Those rings push the fish forward, giving extra thrust. They say that according to aerodynamics, bumblebees shouldn't be able to fly, but they do because they masterfully exploit these microvortices. The physics of hydrodynamics and aerodynamics are universal, so alien bees will buzz and flap their wings on roughly the same principles. There are other methods. Microscopic creatures can cover themselves with thousands of tiny hairs, cilia, and row in synchrony, but that only works for tiny animals. Squid and octopuses invented jet propulsion. They take in water and squirt it out backward, getting a powerful thrust great for escaping predators. Given that their ancestors ruled the oceans for hundreds of millions of years, jet propulsion is a super successful life hack. So we might well meet aliens that move by jet. And smart animals also learn that the fluid itself moves. The sun or volcanoes heat it, creating currents and rising thermals. You can just relax and drift like plankton, or you can surf. Think of an albatross. It's heavier than air, but it sets its wing at the right angle, and the wind creates lift. That's exactly how airplanes fly. Engines push forward, and air flowing over the wings lifts the plane. An albatross can soar for hours without flapping. So no matter how strange alien animals may look, if they live in oceans or thick atmospheres, they obey these laws. They flap, they jet, or they soar. What about moving on solid ground? Gravity pulls everything down, so a solid surface exists on most habitable planets. Pushing off a solid surface is far more efficient than flailing in water or air. But here the enemy is friction. Try crawling without lifting your body. Hard, right? Friction eats energy. That's how the first primitive creatures moved, and how slugs and snails still move, laying down a trail of slime. But a slug can't outrun a cheetah. To beat friction, you need to lift your body off the ground. And for that, nature invented legs. Legs are such a brilliant life hack that they've evolved many times, along completely different paths. Look at a spider and a cat. A spider's legs are hard tubes, an exoskeleton with muscles inside. A cat's legs have hard bones inside and soft muscles outside. The construction is completely different, but the function is the same. Lift the body above the ground and provide leverage for fast running. The important conclusion: animals on other planets will likely have legs. They may not be built the way we're used to. On Earth, there are very strange legs. Velvet worms walk on soft, fluid-filled bags, and sea urchins and starfish move on hundreds of tiny hydraulic tube feet, each foot moving independently, creating a chaotic but effective motion. A sea urchin crawls slowly, but imagine a planet where the surface is covered with sharp, glass-like stones, or where the ground is incredibly slippery, like oiled Teflon. Ordinary legs would be useless. They'd be cut or slip, but hundreds of tiny suction cup feet would work perfectly. We often take for granted one thing when thinking about animals. Almost everything on Earth, from a fly to an elephant, has a left and a right side, which also means a front and back. That's called bilateral symmetry. Only a tiny minority of species, sponges, corals, jellyfish, starfish, lack it. The other 90% of species are symmetrical. Why? Because if you need to crawl purposefully forward over solid ground, it's advantageous to have a distinct front end where sense organs and mouth are concentrated, and specialized limbs along the sides for efficient propulsion. Bilateral symmetry is a superpower for directed movement. It allows incredibly efficient undulating motion. Think of a snake slithering, a ray swimming, or a centipede moving its legs. No shapeless or round creature could compete in speed and grace. So most fast-moving aliens will also be bilaterally symmetric. They'll have a face looking forward in the direction of motion. Wait, what about jellyfish and starfish? Why did they abandon bilaterality? Because jellyfish don't need it. They drift lazily in the ocean and catch plankton. Yes, fast turtles eat them, but in their ecological niche, being simple and energy efficient matters more than fast swimming. Sea urchins and starfish are a detective story. Their ancestors were bilaterally symmetrical. Their tiny larvae still swim like normal tadpoles with left and right. But when the larva settles to the bottom, half of its body dies, and it turns into a five-pointed star or a ball. Why? The answer lies in their hydraulic tube feet. When you move on thousands of independent microfeet over uneven or sticky ground, you don't care which way is forward. You just flow in any direction. In such specific conditions, bilateral symmetry only gets in the way. Now let's apply all this to the two most promising worlds in our solar system, Saturn's moons. Enceladus is an icy ball with a salty ocean up to 30 kilometers deep hiding under its crust. There are hydrothermal vents on the ocean floor, so there's energy. If life exists there, it will behave by rules we understand. The fish or squid of Enceladus will flap fins or use jet propulsion. And the ecosystem could be astonishing. Right under the ceiling, at the boundary of the ocean and the ice crust, animals there should be lighter than water, so gravity presses them upward against the ice. That's an upside-down world. Crab-like things will scuttle across the ice ceiling. Predators will hover in the water column, looking up for prey. The only problem with this inverted world is dead animals. They're heavier than water and will sink to the depths, depriving the ceiling ecosystem of nutrients. Now look at Titan. It has real rivers, lakes, and rain. Only it's minus 180 degrees Celsius, and instead of water, liquid methane flows. Methane is 6 times more fluid than water. Swimming in a Titan lake would feel more like flying in our thick air. So far we've talked about bodies. But what about communication? Imagine walking through a forest. Sounds come from everywhere. Birds singing, leaves rustling, something squeaking in the grass. You see a bird hopping on a branch. You feel a mosquito land on your arm. You smell wet earth. Our world is full of signals. We have 5 senses, and we constantly use them to read information. Animals do this simultaneously across multiple channels. But why so complicated? Why see and hear at the same time? First, it's reliable. If it's pouring rain and you can't hear, you can see danger. In pitch darkness, you can hear it. Redundancy saves lives. Second, it gives more information. Your dog might just bark, but if you add the visual of its posture, you understand its mood much better. Why do we talk with sounds? Among all the smells, touches, tastes, humans chose sound for language. Is that just an earth quirk? Or is there something special about sound that makes it the ideal cosmic communication channel? To understand, think about what good communication needs. Communication is when one individual sends useful information and another decodes it. The signal must carry a lot of information. If your only way to communicate is facial expressions, you can't write poetry or explain a theorem. The signal must work over distance. Touch is great for bonding, but to warn the pack about a leopard, you'd need to get close, stupid, and dangerous. So most animals choose sound. Sound has 3 colossal advantages on Earth, and likely on most other planets. First, it bends around obstacles. Light travels straight. If a bird is behind a bush, you can't see it, but you can hear it. Sound waves are long, so they easily curve around trees and rocks. Second, sound is fast. In air, it moves at 340 meters per second, more than enough for animal communication. Wolves need to coordinate and attack quickly, and sound works perfectly. Third, sound is extremely information-rich. It can carry many different frequencies at once. Of course, sound has a drawback. It needs a medium. In space or on Mars with its thin atmosphere, you can't chat. But on any planet with a thick atmosphere or oceans, sound will be king of communication. But here's a paradox. Humans, birds, dolphins, wolves all use sound brilliantly. Yet our closest relatives, gorillas and chimpanzees, are almost mute. Scientists have tried for years to teach chimps to speak, but their vocal apparatus simply can't do it. That means our common ancestor with apes, only 8 million years ago, couldn't talk either. Birds and wolves, on the other hand, sing and howl. So human speech is not some ancient primate heritage. It's a recent evolutionary invention that we developed independently, simply because sound is a damned convenient tool. Nature keeps coming back to sound when it needs to build a complex society. Alien nature will likely do the same. Our common ancestor with chimps probably didn't chat at all. They communicated visually, with postures and gestures. You can teach zoo apes complex sign language. They even sometimes talk to themselves in gestures when no one's around. So why didn't a full visual sign language evolve in nature before humans invented it for the deaf? Actually, visual signals are everywhere. Peacock tails, the bright colors of poison frogs, the threatening yawn of a macaque, the famous bee dance. Vision appeared very early, about 700 million years ago. As a communication channel, light has powerful pluses. It's instantaneous. It gives incredible precision. Light travels in straight lines, so your eyes can see details from kilometers away. But the pluses end there, and harsh reality begins. Light can't bend around obstacles, we already said that. In darkness, light is useless unless you're a firefly. Light also scatters quickly. Even in the cleanest water or air, you couldn't see a hand gesture hundreds of meters away. And imagine Jupiter, wrapped in dense methane clouds, visibility zero. Some animals try to get around this. Fireflies or deep-sea fish flash like Morse code. But you can't say much with Morse, miss one flash and the meaning is lost. The most amazing visual communicators on Earth are cuttlefish and octopuses. They can instantly change the color and pattern of their skin. Stunning psychedelic displays. But even they don't transmit complex thoughts. They mostly show emotions or hypnotize prey. Humans also use body language constantly and read our dog's posture well. But this language is too imprecise and context-dependent. There's no universal dog sign language dictionary. So the visual channel turned out to be too vulnerable and unreliable to become the basis for complex language. But wait, we always think of visual communication as linear. One gesture, then another. One flash, then the next. We're used to our own language being sequential, words one after another. Read left to right. What if visual language could work completely differently, not in time, but in space? Look at Leonardo da Vinci's The Last Supper dash. It's not just a set of blobs. The placement of each figure carries strict meaning. That's spatial syntax. Could aliens communicate with pictures? Absolutely. Recall those cuttlefish, their patterns aren't random. They have a visual syntax. Now imagine a civilization of highly evolved alien octopuses. They could communicate by flashing incredibly complex 3D holograms or color patterns. Instead of saying, "I went to the store and bought food," they could instantly show a complex picture where the arrangement of spots conveys the entire idea at once, in a fraction of a second. Understanding such a language would be incredibly hard for us because we're used to linear thinking. But that doesn't mean we should dismiss the visual channel. On a planet with different conditions, it might become the basis for something far more powerful than a peacock's tail. Even so, there's a catch. Drawing a detailed picture of a shark when the shark is already nearby takes too long. It's faster to flash red. Abstraction always wins for speed. Incidentally, that's true not just for vision. Our words are also abstract. The sound dog doesn't look or sound like a dog. If an alien heard the sound dog, they'd never guess it meant a furry animal with a tail. Why is that? Danger signals need to be as clear and distinctive as possible. White-nosed monkeys give different alarm calls for leopards and eagles. They can't mimic the leopard's roar because their throats are small. But more importantly, if the signal for leopard sounded like the signal for eagle, monkeys would get confused and die. So evolution forces words to be abstract but maximally distinguishable. So likely, alien language will also consist of arbitrary sounds or flashes. Now let's talk about the most underrated communication channel: smell. It's the oldest way to communicate on Earth. Even bacteria billions of years ago could sniff out chemicals in the water and swim toward food. All multicellular life is built on chemistry. Our cells talk to each other with chemical signals. In the animal world, smells are everywhere. Dogs, ants, bees constantly exchange smells. Food here, enemy there, I'm ready to mate. So why don't we write poetry with smells? Why no chemical language? Maybe there aren't enough smells to make a rich vocabulary? Not at all. Our nose has about 400 types of olfactory receptors. Dogs have 800, rats 1,200. From combinations of these hundreds of receptors, you can create an astronomical number of different smells, more than atoms in the universe. In terms of channel capacity, smell is no worse than sound. Our brain could process chemical speech as easily as sound. So what's the problem? Speed. Light travels instantly. Sound travels at 340 meters per second. How fast does smell travel? Creeps. The speed of smell is the speed of diffusion or the speed of wind. Even in a strong storm, smell moves at only about 15 meters per second. On a calm evening, a message from your neighbor might take a full minute to reach you. Imagine a pack of wolves that needs to urgently say, "The deer turned left." By the time the smell arrives, the deer will be over the next hill. Or imagine trying to reply to a smelly message while standing against a strong wind. Your answer will just blow away. That's one-way communication. So a chemical language is only good for very short, simple messages. Building a complex civilization with literature and science on that seems unlikely, unless aliens communicate cheek to cheek in a perfectly still environment. There are creatures on Earth whose communication is so fantastic it seems like outright telepathy. Electric fish, South American knifefish, and African elephantfish. If we want to imagine truly exotic aliens, we should look at them. Life is electricity. Every cell in your body works by moving electric charges. Since every creature has electricity, evolution was bound to invent a way to detect it. Electroreception exists in sharks, rays, salamanders, and even the platypus, which hunts in murky water with its eyes and ears closed, scanning with its bill. But knifefish and elephantfish go further. They don't just passively detect fields, they generate their own. They have special organs made of modified muscle cells that work like a stack of batteries. The fish creates an alternating electric field around itself and uses it for two amazing things. First, it sees with it. Any rock or other fish distorts the field, and the fish's brain reads those distortions. We can't even imagine what that electric world looks like inside their heads. Second, they communicate with it. By changing the frequency and rhythm of electric pulses, they transmit a wealth of information: who they are, what sex, who's boss. From a physics standpoint, the electric field is an ideal candidate for complex language. It's fast, it precisely indicates where the sender is, and you can pack huge amounts of data by varying frequencies. So why doesn't any fish quote Shakespeare in electric language? And why hasn't this superpower spread to land? Two reasons. First, it's insanely expensive. Generating a powerful field and analyzing the reflected signals burns a huge amount of energy and requires a big brain. Evolution won't invest that unless there's no other way to survive. For example, in the absolute darkness of murky tropical rivers where eyes are useless. It's a costly specialized tool. Second, physics. Electric fields propagate well in water, especially fresh water. But air is an excellent insulator. On land, you can't create an electric bubble around yourself for communication. Current won't flow. Platypuses and echidnas get around this by covering their bills with moist, conductive mucus, but that only works at close range. So on Earth, electric language remains the domain of a narrow group of fish in specific conditions. What does this mean for aliens? On planets with dark subsurface oceans, electric or acoustic communication will be the primary means of contact. Eyeless aliens there might well create a highly developed culture, communicating with complex electrical impulses. On planets like Mars, with its thin atmosphere where sound doesn't travel and electricity doesn't work, evolution will bet on vision or chemistry. We humans love to think of ourselves as the pinnacle of creation. Civilization, rockets, Shakespeare. Animals are just animals. But if we want to understand what alien intelligence might look like, we have to come down from the heavens and ask a difficult question. What even is intelligence? For centuries, people tried to measure intelligence and invented IQ tests, but the problem is they're horribly anthropocentric. We measure everyone by ourselves. If we meet aliens who built a radio telescope but think completely differently, will we recognize them as intelligent or decide they're just weird biorobots? To avoid missing our cosmic brethren, we need to look at intelligence not through human eyes but through the eyes of evolution. Evolution doesn't do anything for no reason. Intelligence is a tool for solving problems. In a world with limited food, limited space, and plenty of predators, those who can adapt survive. Even a primitive amoeba crawls toward where food smells stronger. That's a tiny step toward intelligence. It's not just charging ahead, it's reacting to the environment. But the main job of any intelligence is prediction. Whose bones are those? Is winter coming? Where to hunt? The brain is a prediction machine. Humans have taken this art to the absolute. We can run a simulation in our heads of how a rocket will fly to Jupiter without building the rocket. We predict the consequences of our actions without doing them. But the essence is the same. We, a bat, an octopus, all use our brains to predict what the universe will do next second. We just live in a world of visual objects. The bat lives in a world of echoes. The philosopher Thomas Nagel once said, "We can never know what it's like to be a bat. Our worlds are too different, let alone aliens." In science, there are two views of intelligence. One, intelligence is a set of narrow specializations. The bat is a genius at catching mosquitoes in the dark. The bee is excellent at building honeycombs. The archerfish perfectly shoots down beetles with a water jet. Each has its own superpower, tuned to a specific environment. If so, alien intelligence will be so specific that we'll hardly find common ground. The second view, intelligence is a universal computing system. If you're smart, you're good at both math and music. Scientists long tried to prove this with IQ tests, but today those tests are widely questioned. They depend too much on culture and upbringing. Making an octopus take an IQ test is a mockery. But when an octopus unscrews the lid of a jar from the inside, you realize this creature is incredibly smart. So what unites a smart octopus, a dog, and a human? The answer is simple: flexibility and the ability to learn. Remember Pavlov's dogs. A bell rings, saliva flows. The dog linked a neutral sound with food. That's a brilliant evolutionary hack. Being able to predict the appearance of resources by indirect signs. Or training a dog sits on command to get a treat. That's something that doesn't exist in the wild. The command sit has no connection to meat, but the dog showed flexibility. It understood the rules of the game and changed its behavior for a reward. Almost everyone can learn. Rats run mazes, fish recognize faces. Scientists recently taught bumblebees to play mini-soccer, rolling a ball into a goal. If the ability to link cause and effect and change behavior is so widespread on Earth, it must be a universal evolutionary law. Instincts are hardwired programs. The ability to learn a new trick, that's the basic building block of intelligence. If we meet aliens, they might look like giant amoebas or bats. But if they're intelligent, they will certainly have this superpower: the ability to learn new things and predict the future. Many biologists would argue that intelligence is not just training and learning in a sterile lab. In the wild, chaotic nature, an animal is bombarded with conflicting information. And here two inconvenient facts emerge. First fact: genius arises in scattered spots. In 1960, Jane Goodall made a sensational discovery: chimpanzees make fishing rods from twigs to catch termites. That was a shock because tool use was thought to be uniquely human. On the island of New Caledonia, crows don't just make hooks from twigs to extract grubs. They make tools to get other tools. They can plan a multi-step sequence. So did this incredible intelligence of crows and chimps come from a common ancestor? But their last common ancestor lived 320 million years ago, when giant dragonflies ruled. If it was so smart, why are lizards, ostriches, and antelopes also descended from it so dumb? The answer: the intelligence of crows and chimps evolved completely independently, just like dolphin intelligence and human intelligence. Evolution doesn't hand out general intelligence from one bucket. It sculpts specialized minds for specific tasks. Second fact: different skills live in different parts of the brain. Take birds. A mockingbird is a living tape recorder. It can memorize and reproduce hundreds of other bird songs. Phenomenal learning ability. Now take a chickadee. It sings a simple song, but in autumn, it hides thousands of seeds in different places in the forest, and in winter finds them without error. A human couldn't do that. These two kinds of genius are handled by completely different parts of the tiny bird brain. Singing in one region, spatial memory in the hippocampus. Interestingly, London taxi drivers who have to memorize the city map also have an enlarged hippocampus. So intelligence is not a single substance. It's a set of specialized tools. How then do creatures like us, capable of building spaceships, arise? Probably, human intelligence is simply the ability to combine those narrow specializations. When environmental unpredictability goes through the roof, those who can link memory skills with motor skills and social skills survive. The synergy of these modules gives the spark of reason that eventually leads to a telescope. The aliens we could contact will have gone through the same path. from narrow specialists to universal integrators. We humans are somehow convinced that aliens will be brilliant mathematicians and scientists. Philosophers think they'll be philosophers. We always judge by ourselves. Since the 1960s, it's been believed that mathematics is the universal language of the universe. We even sent plaques on the Pioneer probes showing our position relative to pulsars, using the language of math and physics. It seems logical a triangle is a triangle on Alpha Centauri 2, and pi is the same for everyone. But is that so? Some strongly doubt it. Our mathematics grew out of our physical experience. We live in a three-dimensional world and for millennia ran across a flat savanna throwing spears in parabolas. We intuitively understand Newtonian geometry. But a creature the size of an ant, living on the surface of a tiny ball, would find our mathematics very different from its own. An ant can walk around its little planet and perceive it as flat. In a world where you can only walk on the surface of a sphere, pi is not 3.14. Moreover, our Earth mathematics didn't develop out of boredom. We needed to build straight temples, strong aqueducts, then accurately calculate catapult shots and rocket trajectories. Our math is soaked in engineering. If aliens live in an ocean and don't need to build stone houses, if they're peaceful and don't throw stones, then the math we're so proud of, which we think is the ABC of the universe, might seem as exotic to them as their system of smells is to us. The ability to count is a huge evolutionary bonus. Even fish and pigeons can tell more from less, but that's not yet mathematics. The transition from more/less to a precise understanding of number is hard. Chimpanzees can be taught numerals, and the famous parrot Alex could not only talk but actually count objects. Even if they were different colors and shapes, he understood the concept of number. So why are such abilities found in only a few species? Likely, powerful intelligence arises in leaps when the environment changes abruptly and you need to get smart fast to survive. We fear that aliens will be super intelligent. That's logical, we invented radio only 100 years ago. The chance of meeting a civilization at the same level of development is tiny. They're probably millions or billions of years older. But does that mean their biological brains will be bigger and smarter? Not necessarily. Why evolve biologically if you can create a computer that thinks for you? Once a civilization reaches a technological peak, biological evolution of intelligence stops. There's also the possibility of a hive mind. Look at a school of fish or a bee colony. A single bee isn't very smart, but the colony as a whole makes complex decisions, acting as one brain. Theoretically, aliens could merge into a single supermind, but that would require an incredibly complex and fast communication system between individuals. Sociality and tool use seem to be both evolutionary prerequisites and consequences of intelligence. They're so intertwined that it's pointless to ask which came first. But the decisive role in the mechanism of intelligence evolution was probably played by the interaction between them. And the logical endpoint of intelligence development should be either an external brain, like a computer, or a continuation of biological evolution of the individual, even to the point of becoming what we'd call a supermind. So far, we've discussed aliens as if complex life in the universe can only arise one way, through natural selection, blindly, by trial and error. But let's be honest, there's a second path. Life can be created artificially. We're already on the threshold of that. We make neural networks, genetically modified bacteria, artificial meat. In a few hundred years, we may have robots indistinguishable from humans. Alien civilizations millions of years older have probably already mastered this. The question is, if life is artificial, do the same evolutionary laws apply? Natural selection seems terribly inefficient. Millions of gazelles must be eaten by lions before one gazelle is born with slightly longer legs. Millions of flies must die before one randomly mutates to become poisonous. Slow and uncertain. What if life knows where it's going? What if a robot gazelle can just download an update and instantly run faster? Sci-fi loves scenarios where artificial life spins out of control. There's a famous Soviet story, Crabs Walk on the Island, about self-replicating robot crabs that started eating each other for spare parts and evolved into steel monsters. Mathematically, it's possible. If a bacterium divides every 20 minutes, after 72 hours, the mass of its descendants would exceed the mass of the entire universe. That doesn't happen in reality. Why? First, resources run out. Even robot crabs need metal. Second, as soon as something becomes too abundant, something else evolves to eat it. Ecosystems tend toward balance. But what if alien AI learns to bypass these laws of nature? What if they create beings that evolve by Lamarckian rules? Jean-Baptiste Lamarck, before Darwin, proposed that animals could pass on acquired traits to their offspring. For example, a giraffe stretches for high leaves, its neck lengthens a bit during its life, and it gives birth to a baby with a longer neck. That sounds logical and extremely efficient. Why wait for random mutations when you can directly encode beneficial experience into DNA? But science has shown that on Earth, life doesn't work that way. August Weismann cut off mice tails for generations, but a tailless mouse was never born. Now imagine a planet where Lamarckian laws work, where software or alien DNA can update in real time and be passed to offspring. Evolution there would race at breakneck speed. So why didn't Earth life take that path? What's the catch? We usually think evolution works by mutation, bam, and you grow a third arm. But actually, a large mutation is almost always a catastrophe and death. If a giraffe suddenly grew an extra neck vertebra, its blood vessels and nerves wouldn't cope, and it would die before birth. Evolution doesn't work by crudely adding new parts. It fine-tunes what's already there. Stuart Kaufman gave a great analogy. Imagine you're climbing a hill at night in thick fog. The hill represents fitness. You can't see the full landscape, but you can take small steps uphill. That's natural selection. Now imagine you're given a teleporter that randomly throws you 100 meters in any direction. Would you use it? If you're on a flat plane, maybe nothing to lose. But if you're already on the slope of the hill, a random 100-meter jump will almost certainly throw you into a valley. Evolution is climbing the slope. And in biology, as in robots, one rule holds. If it works, don't fix it. Sudden radical changes in a complex organism almost always lead to fatal errors. So even artificial intelligence will likely evolve slowly, step by step, testing small changes rather than rewriting itself entirely in each generation. Meaning it will obey the same Darwinian laws as we do. Scientists decided to test whether natural selection is really worse than Lamarckism. They created a computer simulation with two types of bots. Darwinian bots were born dumb, learned on the fly, and the most successful survived and reproduced. Lamarckian bots were born already with their parents' downloaded neural nets, knowing where to find food. Who won? It depends on the environment. In a stable world, Lamarckian bots crushed the Darwinians. Being born with a ready-made survival manual is a cheat code. But when the scientists made the virtual world volatile, changed the rules of the game, Lamarckian bots began to die off rapidly. They were born with a rigid belief that, say, leaves on this tree are tasty, but the leaves suddenly became poisonous. Lamarckian bots had no mechanism to forget outdated parental instructions. They blindly followed the manual and perished. Earth's history is a series of horrific catastrophes and global climate shifts. If Lamarckian creatures ever existed on Earth, they would have died out at the first ice age. Only the somewhat dim but flexible Darwinists survived, adapting to a new world over generations rather than through rigid parental instructions. For Lamarckism to work in a changing world, an organism would need a powerful brain. Primitive bacteria and early life forms couldn't afford that luxury, so natural Lamarckism is practically impossible in the universe. But wait, what if aliens or we in the future create artificial life, robots that reproduce and evolve on their own? If we design life from scratch, we would certainly want it to be super Lamarckian. We'd want our robots not just to copy themselves, but to self-improve. Biological evolution can't do that. Here's a simple example. We have a recurrent laryngeal nerve that goes from the brain to the larynx. In fish, it's a short, direct path. But in giraffes, over millions of years, the neck elongated, while the nerve remained hooked on a blood vessel near the heart. So in a giraffe, that nerve goes 2 meters down the neck and 2 meters back up. No sane engineer would design that. An artificial superorganism would immediately fix that bug. The interesting thing is that we humans already use this Lamarckian cheat code. Not in our genes, but in our culture. We pass knowledge, technology, and language to our children. We can say, "Mom, your pie recipe has too much sugar. ChatGPT suggests a healthier one." We can abandon old ideas and invent new ones in a single generation. The evolution of ideas works Lamarckianly, and that's why it moves at breakneck speed. Without it, we wouldn't have built rockets. Animals also have culture, but in us this ability is taken to the absolute. We don't need to wait millions of years for evolution to narrow the female pelvis or widen it for big-headed babies. We invented C-sections and epidural anesthesia. We passed science, medicine, and laws from generation to generation, discarding outdated ideas. It's this cultural evolution that allowed us to leap forward in just a few hundred years. Now imagine we create perfect robots. They have no wisdom teeth that hurt, no appendix that gets inflamed, no stupid recurrent laryngeal nerve that makes a 4-meter detour. They are designed perfectly. Does that mean their world will be a paradise without problems, conflict, or death? No. The mathematics of game theory is ruthless even to perfect machines. Suppose philosopher Nick Bostrom is right and the universe is taken over by a superintelligent AI whose only goal is to produce paperclips. Trillions of perfect bots work tirelessly, mining or in stamping clips. Their world has no music, no art, no sex, just paperclips. But a program is code. Code has errors, mutations. Eventually, one bot, due to cosmic radiation or memory corruption, will change its code. And it will suddenly decide that the most efficient way to make paperclips is to melt down other bots. As soon as a selfish individual appears in a perfect altruistic society, it starts winning rapidly, like a cancer cell in a body. A war of bots begins, competition returns, evolution resumes. So a supermind does not mean invulnerability to the laws of mathematics. What about immortality? Almost all of us dream of living forever. Billionaires invest fortunes in anti-aging drugs. Alien AI, it would seem, could easily replace worn-out parts and live forever. But evolution, even technological evolution, hates immortality. Why? First, no room for new ones. If no one dies, the planet quickly overfills, and without generational turnover, there's no development. An immortal bacterium would never become a human. Second, the world changes. No matter how perfect a robot is, if an asteroid hits tomorrow or the star cools, the old design might become inefficient. Those who can quickly restructure through generational turnover survive. Third, everything has a cost. It's the law of compromise. You can make titanium armor and eternal batteries, but you'll become heavy and slow. In a world where all turtles are immortal, a fast hare that lives only 1 year will grab all the resources. On Earth, there are Australian marsupial mice. The males mate non-stop for 2 weeks and then literally die of exhaustion. From an immortality perspective, that's a failure. From an evolutionary perspective, it's a super success because they pass on maximum genes. Any AI will face this compromise. Why build a battery that lasts 1 million years if a drone with a 100-year battery flies twice as fast and collects more resources? Looking at the cosmos, we don't see armies of self-replicating probes. Apparently, the mathematical laws of competition, selfishness, and limited resources restrain steel hordes as effectively as colonies of bacteria. But there is a wild, scientifically plausible idea: directed panspermia. What if billions of years ago, some benevolent alien civilization came to an empty Earth and simply poured a bucket of RNA molecules into the ocean, sowed seeds, and left? Since then, we've been stewing in the cauldron of natural selection. We evolve blindly, suffer disease, and get wiped out by asteroids. We seem 100% natural, but perhaps this whole brutal Darwinian process was just an incubator. The aliens knew that Lamarckian robots would die at the first climate change. They knew the best way to create robust intelligence is to put it through billions of years of a natural meat grinder. Perhaps that was their grand plan. Lamarckian artificial organisms couldn't survive the early stages of evolution, but they were destined to mature one day. Our creators understood that and had the patience to wait for the results of their experiment. It's an unlikely scenario, but it allows the possibility that other planets are populated by artificial life forms that are nevertheless indistinguishable from the expected products of natural selection. For millennia, we thought we were unique. It was perfectly clear who is human and who is not. But science has begun to blur that line. We have Neanderthal and Denisovan DNA in us. Animals can be friends, feel sadness, make tools. Now imagine we look into space and find a civilization. In science fiction, aliens often look human, mainly because it's cheaper and easier to film. But if the biological laws of the universe are truly universal, what if Hollywood is right? What if we find beings that walk on 2 legs, build houses, love their children, write poetry, and go to war? Would they essentially be human? Let's separate the issues. There's the legal concept of personhood, and there's the biological concept of being human. Would aliens be persons? That's a question for psychologists and lawyers. On Earth, we still can't agree. In the past, some human races weren't considered persons and were sold into slavery. Now activists file lawsuits to recognize chimpanzees tortured in labs as persons, or Happy the elephant who recognizes herself in a mirror. Courts have so far refused. Society isn't ready to give animals human rights. What about artificial intelligence? When will a computer become a person? If we ever download our consciousness onto a flash drive, can we be deleted without committing murder? Personhood is a matter of our morality and agreement. But being human is a biological question. The simplest answer, human is just the species Homo sapiens dash. Everything else is not human. End of story. But scientifically, that's a very bad answer. First, it's a logical dead end. Defining yourself by yourself is meaningless. Kant said, to understand what a rational earthly being is, we need to compare ourselves with a rational non-earthly being. Otherwise, we're just stewing in our own juice. Second, the concept of biological species is very fuzzy. We're taught that a species is a group that can interbreed and produce fertile offspring. A cat can't breed with a dog. But nature is full of exceptions. Wolves, coyotes, and jackals look different, live differently, but they interbreed freely. Species don't appear by snapping fingers. It's a long, gradual process. Richard Dawkins gave a great example. The boundary between us and apes seems sharp only because all the intermediate links are extinct. Imagine all your ancestors lined up in a row. You'd walk along and see no difference between generations, but at the end of the line would stand a hairy Australopithecus. At which great-grandfather did the human end? There's no answer. Moreover, we modern humans aren't even a pure Homo sapiens species. Our ancestors actively interbred with Neanderthals and Denisovans. Almost all people except indigenous Africans have up to 4% Neanderthal DNA. We are a genetic cocktail of different ancient human species. So if we can't even clearly define where non-human ends and human begins on our own planet, how will we decide for aliens? Let's try from another angle and define humans by a set of traits, by what they do and what they can do. The first candidate is reason. We like to call ourselves Homo sapiens, wise. But what is reason? If reason is the ability to solve problems, then the crow that bends wire into a hook to get food from a bottle is also reasonable. The octopus that unscrews a jar from the inside is reasonable. Even a slime mold with no neurons finds the shortest path through a maze. Reason is too fuzzy a criterion. Maybe it's language. We are the only ones who can talk about the past, the future, and things that don't exist. A bee can say through dance, honey is 100 meters north. But a bee cannot say, remember that honey we found last year? Still less can it say, what if honey runs out one day? That's called displaced reference, the ability to talk about things not here and now. That's a powerful candidate. But is it enough? Second candidate, theory of mind, the ability to understand that another creature has its own thoughts, desires, and knowledge different from yours. You know your dog is hungry, but does your dog know that you know he's hungry? Chimpanzees seem to have this. They can deceive each other. To deceive, you need to understand that the other doesn't know something. But chimpanzees can't discuss with a friend why they deceived a third. They lack reflection upon reflection. Third candidate, cumulative culture. Not just mom showing how to crack nuts, but a chain great-grandfather invented, grandfather improved, father added, son rethought. Each generation stands on the shoulders of the previous. No chimpanzee has ever improved its termite fishing stick in 1,000,000 years. But we went from stone axe to Large Hadron Collider in 10,000 years. Cumulative culture is the ratchet that prevents backsliding. Invent the wheel. It's forever in the bank of civilization. That's the Lamarckian evolution of ideas. Fourth candidate, imagination, the ability to model in your head something that never existed. Draw a unicorn, invent a god, write a constitution. Money is imagination, the state is imagination, human rights are imagination. Not a single atom in the universe knows what a euro or democracy is. It exists only in our heads and works only because we agree to believe in it. Yuval Noah Harari called this the cognitive revolution. The ability to believe in fictional things allowed thousands of strangers to cooperate. Ants also cooperate by the millions, but under a rigid genetic program. We can restructure our entire society in one generation simply by changing the story we believe in. So if we meet aliens who possess all four traits, reason, language, cumulative culture, imagination, would they be human?
Biologically, no.
They might have silicon blood and 8 legs, but functionally they would be indistinguishable from us. They would argue about politics, fear death, and wonder if they are alone in the universe. And here's where it gets really interesting. If convergent evolution is a law, not an accident, then these traits may be inevitable for any sufficiently advanced civilization. Just as eyes evolved independently dozens of times on Earth, so reason, language, and culture may be evolutionary attractors, points toward which any complex life is drawn. Maybe human is not a biological species. Maybe human is a stage of development like a butterfly is a stage of a caterpillar. Any civilization that goes through a long enough meat grinder of natural selection will sooner or later arrive at the same toolkit. A big brain, complex language, knowledge accumulation, and the ability to dream of the stars. If that's true, the universe could be full of humans. They will look different, breathe different gases, live at different temperatures. But inside, in what truly matters, they will be us. And then Captain Kirk's phrase takes on a whole new meaning. We are all human, not because we share the same DNA, but because the universe keeps reinventing the same solution to the same problem: how to survive, understand the world, and pass that understanding on. So next time you look at a crab, whether it's a real one or a fake, remember, evolution has a favorite shape. And maybe, just maybe, that shape isn't only about shells and claws. Maybe intelligence itself is another crab. And out there, somewhere, another species is just tucking in its tail, flattening its shell, and beginning to ask the same question we've been asking for millennia. Are we alone? If you made it this far, you're a true explorer. Hit like and subscribe, and in the comments, tell me, do you think aliens will look like us on the inside?